All right, the least squares regression line is it's a calculation that I kind of shield you from, but I wanted to give you a conceptual understanding of what's really going on. If we have a data set here, whatever that is, if we draw a line through the data, whatever that line is, and we find how far away each data point is vertically off that line, okay? So for instance, let's say this one looks like it's about 1 unit off, right? Because that's at 5 and that's at 4. That's 1 unit off. So if I go 1 and then make a square, make it a 1 by 1, that is the sum, that's the area of that square. And if I add this box and this box and this box, add all the boxes together, I get this little sum of squares piece of data. Does that make sense? Now, watch what happens when I manipulate the slope. See how that's changing how much error there is, right? Now, the goal is to do what? Make the error as small as possible, right? So I'm just going to play around with this a little bit and see here. There's 3.65. Okay, now, what's the other thing I can manipulate? Besides the slope of the line, I can change the what? The y-intercept. So I'm going to change the y-intercept here. Notice how that changes how much error there is as well, right? So I'm trying to minimize the sum of the squares. This is called the least squares regression line. So I'm actually just manipulating this line until it works, okay? So let's see here. Let's minimize this. There was 609. So there, I've minimized it on the, and I'm going to do the slope again. See if I can get lower than 3609. Nope. All right. So that's my best guess. Now, there's a formula in your book on how to find the least squares regression. There are ways in calculus to find the least squares regression. And I'm going to hit this button right here. It says show least squares regression. Let's see how close we are. Pretty darn close, weren't we? 3.6 was the least for that one. Okay. So the least squares regression line is just trying to find a line that fits the data and makes the sum of these squares the smallest as possible. And then we can use things like R, our correlation coefficient, to describe a couple things. How well does it fit in the direction it goes in? So if R is positive, it's got a positive correlation. If R is negative, it has a, so I'm going to go data set 2 right here. All right, so there, this looks like it's sloping down, right? So I'm going to change the slope to that, and let's change the intercept up here. See I'm doing this? Looks like down a little more, up a little more here. Oh, there we go. So I'm finding the least squares regression here. It's like, so what do you think? Is that data really close together? Really strong? So is the correlation on this one, or the R value, the correlation coefficient, is going to be even tighter. So this is going to be like negative 0.9 something. The best you can get is 1, or if it's positive, and if it's negative, the lowest is -1. So I'm going to actually hit least squares regression. We were pretty much right on it, weren't we? And now I'm going to go to the data set 3, and let's see here. Let's change the y-intercept. Let's change the slope. This one looks like it's got a positive one again. So that one's got a positive correlation. Now if it's a horizontal line, then obviously the slope is 0, and there's pretty much no correlation, and R is almost 0. So the closer R is to 0, the closer it is to no correlation. And the stronger it is to 1 and -1, the stronger it is positive or negative.